In the last two videos, we derived this formula up above, which says that if you have a geometric series with a constant c and a ratio r, then we can show, and the sum goes from 0 to infinity, that's important, then the sum will converge if the absolute value of r is less than 1, and it converges to c over 1 minus r. And if the absolute value of r is greater than or equal to 1, then the sum will diverge. And we looked at 3 examples earlier on. We looked at keeping track of the total number of coronavirus cases, given that we have 64 on day 0 and then 25% increase each day. And we showed that we could write this as the sum of 64 times 5/4 to the n. And so notice here we have c equals 64. We have r equals 5/4. And because the absolute value of r here is greater than or equal to 1, right off the bat, we know that this is got to be a divergent series. All right, so that is consistent. And again, that makes sense. If you have more cases each day, more new cases each day than you did the day before, there's no way you can end up with a finite number. Eventually, that pattern is going to have to change. All right, so the second example we looked at was the scenario where a ball was bouncing up and down. We said it bounced 1 meter on the first drop, and then each subsequent drop was 3/4 of the previous one. And so the next bounce would be go up 3/4 and then down 3/4, and then the next one after that would go 3/4 squared up and then 3/4 squared down. And so we wrote it as a sum of 2 series, both geometric. One summed from 0 to infinity, and the other summed from 1 to infinity. And so we'd like to use this geometric series result. And so first we'll identify our c. In this case, the constant we had out front was just 1. And the ratio of consecutive terms, the factor that we're multiplying over and over again, is just 3/4. And so since this quantity is less than 1, should be strictly less than 1, we'd say this must converge. And then the question is, what does it converge to? If it converges, that means that as we add it up, it's going to get closer and closer to some particular number. And that means that this ball does not travel an infinite distance. It travels some finite distance, and we'd like to know what that distance is. All right, and so if you look at the first term, this one is already nicely in the form of the formula that we derived earlier. So we would just write the sum is just c over 1 minus r, which is 1 over 1 minus 3/4, or 1 over 1/4, which is just 4. Okay, so that first sum must approach 4. And then the second sum, notice it's almost the same, except the sum starts with n equals 1 instead of n equals 0. So we want to figure out what this adds up to. And we can't apply that formula directly because, again, let me scroll back up. Notice this assumes that we started our sum with n equals 0. But we can modify this slightly because notice the sum from 1 to infinity is the same thing as the sum from 0 to infinity minus the first term. Right? We can just remove the first term from the sum. And since we already know what that first, we know what this is, that's just the c over 1 minus r, which we showed was 4. And we subtract 1, and we find that the second sum is just equal to 3, which means the total distance has got to be just 7. All right, so very important when you're using this geometric series formula, that only applies if the sum starts with 0. If you start at some other number, what you can do is you can just subtract off those extra terms from the formula. In this case, we subtracted 1 to get our answer. All right, one more. This was the scenario where we have a guy, Bob, who spends 90% of what he gets. And then when that money is spent, the people who receive that money spend 90% of that. And so we've got $900 spent by Bob, and then 900 times 0.9 by the next group of people, and 900 times 0.9 squared for the next group. And we'd like to know what's the total amount of spending that's induced by this original $1,000 that Bob received. And we showed that you could write this as the sum from n equals 0 to infinity of 900 times 0.9 to the n. And so our c is 900. The r is 0.9. And so the sum, well, absolute value of r must be less than 1 for convergence. And in this case, it's 0.9. So that's definitely less than 1. So this is going to be a convergent geometric series. And the formula for what it converges to is c over 1 minus r. So 900 over 1 minus 0.9, which means we have 900 over 0.1, or 9,000. So in this scenario, giving Bob $1,000 led to $9,000 in total spending, because he spent 90%, so he spent 900, the next person spent 810, the next person after that spent 729, and so the total of that cascade effect is $1,000 in spending. By the way, you could also ask the question, well, how much did they save? How much will be saved? And in this case, he saves 100, and the next person will save 90, and the next person will save 81, and each person will save, again, 10% of what they received. And so we could say the saving sum would be 100 plus 100 times 0.9 plus 100 times 0.9 squared, and so on, which we could write as the sum of 100 times 0.9, not 0.9. You guys would have called me that if we were in class. He saves, yeah, I guess he does save 90%, so that was okay. And let's see, n goes from, we have 0.9 to the 0 up to infinity. And that, if we use our geometric series formula, has got to be, it looks like the constant is 100 and the ratio is 0.9. And so we would have 100 all over 1 minus r, which is 100 over 0.1, or 1,000. And perhaps that should not come as a surprise. $1,000 was the amount that Bob received in the first place. And so ultimately, if you think about everybody who receives money, a total of $1,000 gets saved, but $9,000 ultimately is what gets spent. So giving him $1,000 induced a whole lot more spending than it did savings. Okay, so this geometric series formula is useful for summing series where we have the form constant times r raised to some n, but we can't apply it to other types of series. So in the next video, we'll look at some other examples where we don't have a geometric series and see under what circumstances we can find a nice summation formula there.